students, welcome back. In today's class, we'll learn about resistivity, how it is different in different types of materials such as metals, conductors and insulators, as well as semiconductors. Before that, in the last class, I have discussed about specific conductance, Ohm's law and so on. Today, I just give you an equation of Ohm's law in vector form. You can note down Ohm's law in vector form. So this is not a derivation from basic beginning. So I'll just do it from the derivation which is already been done. Okay, so this equation has already been derived before. Okay, this equation of potential is already been derived. This is from the equation of Ohm's law. If you go and check the equation, this was the equation where this constant factors were termed as resistance. Okay, this is V is equal to, this is resistance into current. V is equal to Ri, which is the Ohm's law. Now, from here, what we can see is from in this equation, if you take this L towards the other side, then this becomes, okay, this becomes V divided by L is equal to, this part is the resistance into I. Now, the next is V by L is E, which is the electric field, and this next part, this part is the resistivity. Okay, this is the resistivity. I by A is the current density. So in place of V by L, I can write E. In place of this factor, this part, I can write resistivity. In place of I by A, I can write current density. Now the next thing is E is resistivity is the reverse of conductivity. Okay, I hope you know that it's just a reciprocal of conductivity. So in place of resistivity, I am writing 1 by conductivity. So from this equation, what we can write is, we can write J is equal to sigma E. So this is a vector, this is also a vector. So the equation becomes current density is equal to conductance multiplied by electric field. So this is the equation of vectors, Ohm's law in vectors form. Please don't get confused with other equation. This particular equation given over here is Ohm's law in vector form. This has to be in vector form. With this, I'll move on to the topic which is resistivity. So resistivity has a different, temperature has a different effect on resistance. Okay, temperature has different effect on different type of substance. So we'll talk about resistivity. First, we'll talk about metals. Okay, first we'll talk about metals, which are the conductors. Which are the conductors. And in an electrical circuit, we are mainly focused towards metals which are conductors. So, with the rise of temperature, when the temperature increases in a circuit, in anywhere where the temperature increases, automatically what happens? Resistance will also increase. Okay, resistance will increase, current will become less. Same example we can relate it with the filament bulb. When a current flows in a filament bulb, after some time the filament bulb will start getting heated up. Because it is an electronic devices, so those devices will start getting heated. And what happens after they get heated? With the rise of temperature, resistance will also increase. When resistance increases, resistance means blocking of current. When the electrodes are blocked, what happens? The resistance will increase, current will automatically decrease. So now from the equation of resistance, okay, R is equal to, from the previous relation, if you just take the equation, it was M for N E square tau, okay, L by A. This was the formula or equation of resistance which we have derived in Ohm's law. So from here what we can see is R is inversely proportional to tau. Now this is relaxation time, time of an electron. Relaxation time means when electron is moving inside a conductor, it is a time between two successive collisions. When it collides at 2 points, it is the relaxation time. Okay, the time taken for two successive collisions for to move a path, a complete path. This is the time. Now, time is equals to. So from here, what we can see is with the rise in temperature, when the temperature increases, the relaxation time will decrease. Okay, from this we just look at this relation. How it happens is when the time increases, when the temperature higher, the electron starts moving with more energy. It will start moving with faster than before. That means the time which it was taking before, now it will become more. So if the time becomes more from this relation, if this is increasing, if relaxation time is increasing, resistance will decrease. Okay, resistance will decrease. When this increases, resistance will decrease. It's just the reverse. So what happens is, in turn, with the time increases, resistance, with the rise in temperature, resistance also increase and electrical conductance will decrease. So if you draw a graph for this one, the graph is quite simple. Graph of resistance versus time. So with the increase in time, what happens? First it was increasing slowly. After some time, it will increase drastically. So this is the graph. And for this topic, the graph is very important. Okay, you need to understand the graph. So this straight line means both are increasing together. So initially it was not increasing as much, but afterwards it has increased in a large manner. Now the next is resistivity in case of alloys. In case of alloys. I hope you know what an alloy is. So in the case of alloys, it happens the same. With the rise in temperature, resistance will also increase. Simple what happens in metals, the same thing will happen in alloy, but the graph will be a bit different. It is not the same. It won't increase that much, but it should increase in a different manner. Okay? The graph will look like this. This side is temperature, this side is resistance. So with the rise in temperature, resistance will also increase. This is for alloys. But resistivity of pure metal, which was in the before case, the resistivity of pure metal increases more than that in the case of alloys. You need to remember that. The third one, I am just drawing the graph because graph is important in this question. Now the third one is in the case of semiconductor. The semiconductor has its own way of rising the resistance and decreasing the resistance because it's a totally different substance. It is neither conductor, neither insulator. It lies exactly in the in-between, which behaves like a conductor if some sort of extra potential is given. Okay, we'll learn about semiconductors. There is a specific chapter for that. Okay, so if the temperature rises, in a semiconductor, resistance will decrease. Okay, if the temperature rises, resistance will decrease. Because in a semiconductor, the number of electrons are very less, very few. But on the rise of temperature, on the rise of physical conditions, what happens? The electrons will start moving with more energy. So when the electron starts moving in semiconductor, then there is a sudden rise in the current for a while. Okay, not for a long time, but there is a sudden rise in the current. Now the graph of the semiconductor will be like this. Okay, it will increase this way. Or with the rise of temperature, resistance will decrease. Few examples of semiconductors are silicon, germanium, and so on. Now this is about resistivity. You don't need to go in depth and detail everything which is given in the book. Just go through the basic graph, the topic, and what happens when the temperature rises. That much is enough from this chapter, this topic. Now the next topic is a short derivation for the power. So the topic will be electrical energy and power. Electrical energy and power. So for that I will draw a small circuit. Okay. So this is positive terminal, negative terminal, current will flow this way. This point is A, this point is B, this is a key, this is potential. And the current I is flowing in the circuit. So now we have a basic circuit. Potential is applied by this battery. There is a terminal A and B. A and B can be anything. Can be a resistor, can be a bulb, can be any object given in the circuit. So with the help of when the current flows, what happens? There is some t amount of charge will start flowing. Equation number 1. Charge is equals to current into time. So in t amount of time, q amount of charge will flow from point A to point B. Okay. The next thing is, when the charge flows, there is some amount of work done. Okay. Work done for this charge. While this charge is moving from one point to another, some amount of work has to be done by the battery to make the charge flow. So the work done in moving the charge will be Q into V. If you know the equation of potential, potential is work done per charge. So from this equation, W becomes V into Q. This will be equation number 2. Okay. So this is the amount of work done for this battery to move the charge from point A to point B, not through the whole circuit. Now, if this box over here is a resistor, which has a resistance R. Okay, that it is a resistor with a resistance R. So we know that R is equal to V by I. Okay, R is equal to V by I, or V is equal to I. From the same equation, V is equal to IR. Also, I is equal to V by R. I is equal to V by R. So one by one, what we do is we put the value of V and I in this particular equation of W. What we know is W is equal to, in place of Q, I can write IT. So in place of Q, if I write IT, then equation number 2 becomes, okay, you can write from equation 1 and 2. Okay, from equation 1 and 2, what we can write is W is equals to V I T. W is equal to V I T. Now, first what we will do is we are putting V is equals to IR in equation 3. If I put W is equals to, in place of V, if I put IR, then in this place, okay, I am putting IR, then this becomes I square R T. This is the work done. Okay, read equation number 4. Now the next step, what I'll do is, in place of, I will put I is equal to V by R in equation 3. Okay, in equation 3 again, in place of I am putting V by R. So this becomes V by R into V into T, which is V squared divided by R T. So the equation number 5. So from here what we can see is equation number 4 and equation number 5. Okay, equation number 4 and equation number 5 are the equations of work done when moving a charge from point A to point B. Now with that, we'll talk about power, electric power. So with the help of work done, what we can find is, we can find electric power. If you remember, power is equal to work done per time. Okay, power is equal to work done per time. Now, okay, W was VIT divided by T. So power becomes T gets cancelled, V into I. There are many equations of power. This is one. Okay, topic you can write it as electric power. This is first equation. Now again, in place of V, what I can write is, I can write V is equal to IR. So in place of V, I can write IR. This becomes I squared R. This is the second equation of power. Now again, in the same equation, over in place of I can write V by R, input in equation 1. These things I am going a little fast because the same kind of derivations we have done in class 10 also. So I hope you remember that. If you don't remember, just recall it, and if I am going very fast, do pause the video and make it slow and do it step by step. So again, in place of I am putting V by R in equation number 1. So P is equal to V squared R. This is equation number 3. So these are the three equations of power. These three formulas have to use in different kind of questions where sometimes potential and current is given, sometimes current and resistance is given, sometimes potential and resistance is given. So depending upon the different questions, we will use this formula. So now these equations are only true if energy is transferred into heat energy. Remember this. Whenever some work is done, energy is also transferred in one form from one form to another form. So this equation of power is only applicable when energy is converted into heat energy. Now the value of power. Value of work done. Power, the unit of power is watt. Okay, the unit of power is watt. Now for higher units of power, 1 kilowatt is equals to 1000 watt. 1 horsepower is equals to 746 watt. Remember this conversion. Okay. Okay. So till now we have studied about electrical energy, electrical power, and so on. So for the next things we'll discuss in the next class. So this much for today. Thank you.